today for class 12, that is bar magnet as an equivalent solenoid. That is a bar magnet bar magnet magnet as an equivalent solenoid. This is the topic taken from Magnetism and Matter. This is the topic taken from Magnetism and Matter. Here you see that as an equivalent solenoid. So we are going to draw a solenoid. Here this is a solenoid. This is a solenoid, and we are taking its center, that is at the origin here. We are taking the center at the origin here. So this is x-axis, this is your origin, this is your y, and this is your y dash, and this is your x dash. And your point of observation is somewhere here P. And we are taking a small strip here. Let this be dx, and I current is flowing through it, and the radius of this coil is your A. Radius of this coil is A, and this is at a distance x. This strip is at a distance x, and from here to the point of observation it is r. So we are going to use the Biot-Savart law. According to the Biot-Savart law, your before that, let me write that I current is flowing through this coil. And N is the number of turns per unit length. It is the number of turns per unit length. So here we are going to apply the Biot-Savart law. Here you see according to Biot-Savart law, for a circular loop, the magnetic field at a point r, this distance is x, and this is the radius r for this dl element. So the magnetic field at this point P is dB, that is equal to nu naught I r square by 2 x square plus r square by 3/2. This we have calculated in Biot-Savart law. So we are going to use this formula here. So according to this formula, the magnetic field at this point will be dB for one coil, that is nu naught I, and your radius here, radius is r, your radius is a square by 2, and this distance this r distance is from origin. This r distance is from origin. This is the coil, and this r distance is from origin here. So the distance from here will be your r minus x the whole square, and plus your radius square, that is a square by 3/2. According to the Biot-Savart law, this is for one coil. Now, as in unit length there are n turns, for dx there will be n into dx turn. So magnetic field for this n into dx turn, this will be n dx nu naught I a square by 2, that is r minus x the whole square plus a square by 3/2. This will be your r minus x. This is r minus x the whole square plus a square to the power of 3/2. Now if you take r that is greater than x, and r very greater than a, if you are going to take this, so here your magnetic field, this is n, magnetic field dB, this will be n dx nu naught I a square by 2. These two are neglected, so this will be r square, cancel out r to the power of 3. This will be your Now we are going to integrate it for this whole coil. If you are going to integrate this, this is for the whole coil, that is dB, that is equal to your these are the constant n nu naught I a square 2r square r cube, not r square, this is r cube integrated dx from minus L to L. Here this is minus L length, here this is L, so twice L. So from we are going to integrate it, so we get the value n nu naught I a square by 2 r cube, and this will be 2L. Now let me do one thing, some adjustment here. So your adjustment here is nu naught 2L nu naught n 2L n into 2L, and again I pi a square by 2 pi r cube, 2 pi r cube. So here you see that it is here. Now about magnetic moment M, that is equal to NIA. This is the total number of turns. So this is the total number of turns, this is the area, and this is the current. So this becomes dipole moment, that is magnetic dipole moment. M, that is magnetic dipole moment. This M is magnetic dipole moment. This becomes magnetic dipole moment. So here this will be your nu naught this whole, see, this is the total number of turns, this is the current, this is the area, M by 2 pi r cube, 2 pi r cube. Now a little arrangement, because the constant is nu naught by 4 pi, so this will be 2 nu naught, let me do like this here, nu naught by multiplying 2 numerator and denominator, so this will be 4 pi 2m by r cube. So this is the magnetic field. So this is the magnetic field at this point, and it is same as the bar magnet. So here, see, it has been proved that the bar magnet has an equivalent solenoid. So this is the magnetic field of a bar magnet. Now my next topic is magnetization and magnetic material. Magnetization, that is next topic is magnetization and magnetic intensity. Next topic is magnetization and magnetic intensity. My next topic is magnetization and magnetic intensity. This is my next topic. So here you see that the most important thing here is that a current carrying loop, it is a magnetic dipole. So it has magnetic dipole moment. It has magnetic dipole moment. A current carrying loop is a magnetic dipole, and it has magnetic dipole moment. So here you see that in any atom, the electrons are revolving around the nucleus, so it is a magnetic dipole. So it has magnetic dipole moment. So it has magnetic dipole moment because we know that the electrons are revolving around the nucleus. So electrons are revolving around the nucleus. It is a magnetic dipole, and so there is magnetic dipole moment. Now, if you consider the whole material, now if you consider this whole material, your net magnetic moment, that means if you add this vectorially, if you add all this magnetic moment, add vectorially, the net magnetic moment is not zero. The net magnetic moment is not zero. So here comes magnetization. Magnetization, it is net magnetic moment. It is net magnetic moment per unit volume. It is net magnetic moment per unit volume. It is net magnetic moment per unit of volume. This is magnetization. Now here we know that the magnetic field inside a solenoid. That is B is equal to mu naught n I. That is, n is the number of turns per unit length. We know that magnetic field inside a solenoid is mu naught n I. We know. Now here that is B naught. And if if we place a material, that is a soft iron like this, inside the solenoid, its magnetic field will be, that is B naught plus magnetic, this is the magnetic material. Your total magnetic field will be B naught plus this magnetic material. Now here you see that means the magnetic field increases. When we place a magnetic material inside a solenoid, this is B, it is the magnetic material. If you place it inside the solenoid, your magnetic field increases. So here this B naught, it is proportional to magnetization, that is mu naught M. That is, M is the magnetization, and mu naught, it is the permittivity. It is the permittivity of vacuum. It is the permittivity of vacuum. V-A-C-U, no, vacuum. It is the permittivity of vacuum. So B naught is proportional to the magnetization. Now this is the magnetic field inside a solenoid. Now if we place a magnetic material inside the solenoid, its magnetic field increases, and this is equal to B naught plus magnetic field of the material. That means its magnetic field increases. Now there is another topic, that is magnetic intensity. Magnetic intensity. So here your magnetic intensity, that is B naught by mu naught minus M. This is your magnetic intensity. This is M. This is, let me take, this is the total magnetic field. B by this is the total magnetic field, B by mu naught minus M. Now here you see, this is M, this is H. This is intensity, magnetic intensity H. So here if you take the LCM, mu naught, that is B minus mu naught M. So here again this becomes nu naught H, nu naught H, this is equal to B minus nu naught M. So this will be here nu naught, that is H plus M, that is equal to B. This is your magnetic field. So here you see that the magnetic field, this is the main result, that means B is equal to nu naught H plus M. This is the result. That means the magnetic field, total magnetic field, is caused due to, this is the external factor. External factor, that means what is the external factor? That is the current flowing through this solenoid, and M, it is because of the magnetic material. Magnetic material inside the solenoid. It is because of the magnetic material inside the solenoid. So here, this is the main result. This is the main result it has been drawn. That is your magnetic field, that is equal to nu naught bracket H, H magnetic intensity plus magnetization. So magnetic intensity, because it is because of the external factor, and M, it is the magnetic field due to the magnetic material. Now here again, your magnetization is equal to susceptibility of the magnetic material into intensity, that is magnetic intensity. So magnetization, this is equal to the susceptibility of the magnetic material into the magnetic intensity. Now so here you see that now from this is your result. We are going to get a new result. We are going to place the value of M here. So this will be nu naught H plus, this is susceptibility of the magnetic material into H. This is the susceptibility. It is the susceptibility of magnetic susceptibility. This is magnetic susceptibility. So here this is equal to B. So nu naught H, that will be 1 plus this susceptibility, magnetic susceptibility. So this is B, this is magnetic susceptibility. So here this is nu naught H nu R B. So your magnetic field will be nu naught nu R into H. This is relative, this is nu R, this is relative magnetic permeability. This is relative magnetic permeability, permittivity, sorry, permittivity. This is relative magnetic permittivity. So what here the main conclusion is that this is a solenoid, and inside we put a material of non-zero magnetization. Non-zero magnetization means it is a magnetic material. Means it has been said here BM, it is a non-zero magnetization. Non-zero magnetization. Non-zero magnetization, it means when it is a magnetic material. So if we place a magnetic material inside the solenoid, its magnetic field increases. And another is the topic, that is the magnetic intensity, and magnetic intensity is this, and if you arrange it, we get magnetic field, that is the total magnetic field, that is equal to this. So this means that what is the main conclusion here? This is the magnetic field. It is due to the two factors. One is the external factor H. It is because of the current flowing through it, and M, it is because of the magnetic material. And again, magnetization is also proportional to magnetic intensity, where this is called magnetic susceptibility. This is called magnetic susceptibility. Now, if you place the value of M here, we get this result, and this is called the relative magnetic permittivity. This is called the relative magnetic permittivity.